I request Mr. Balapriyan, Council Member, Chennai Chapter IF, to introduce fifth speaker of the day, Mr. V.Baskar, Sr.GM, Core Shop, Breaks India Foundry Division, to our audience.
Good afternoon. Next speaker is Mr. Baskar, and he is going to talk on the topic Best Practices in Core Manufacturing. Mr. Baskar completed his diploma in mechanical engineering during 1982 and graduated with distinction in mechanical engineering from Vellore Institute of Technology in the year 2005. He joined Breaks India Limited Foundry Division during the year 1982 and taken various roles and responsibilities during his tenure of 40 plus years. He had worked in various roles in Foundry Division. From 2014, he has been heading the core shop activities, responsible for core production and supply of quality cores to all production lines. He is also responsible for subcontractors management and maintenance activities. With his wide knowledge in production and excellent leadership skills, he has played a key role in the growth of Foundry Division. He is actively involved in TQM, TPM practices in the Foundry Division, Certified Internal Quality System Auditor for IATF 16949, ISO 14001-2015 and Environmental Management System 50001-2018 standard. We welcome you, sir.
So I am going to talk about best practices in core making. Why is it necessary? The challenges in the foundry industry is growing complexity of increased complexity of the increased core intensity, reduction of the casting weight, castings walls are gradually becoming thinner, low dimensional tolerances, environmental registrations are on national and international levels, protection of employees' health and safety, high competitive pressure. These are the challenges to the foundry industry. This is the complexity of the cores becoming severe nowadays. So the requirement of the good core, able to withstand erosion, abrasions during handling and metal penetrations, hydrostatic pressure of the molten metal, allow gases to escape easily and minimum generation of gases, collapse easily to leave clean inner cavities, dimensional accuracy and temperature stability. You should have less or no reaction with the metal. Latest quality requirements of the core. Casting cleanliness is measured by the particle weight in grams and particle size of microns. Core quality and its interactions with the metal which causes cleanliness in the castings. These are the latest requirements. Impact of core quality on the castings. Casting rejection due to core-related defects, rework of casting due to cores, lumps, sand fusion, scabs, etc. Casting cleanliness due to core residues. Throughput time increases because of the rework. These are some of the defects, core-related defects, veins, scabs, blowholes, fins, erosion, metal penetration, white film. These are some of the defects which causes because of core. So this is the historical development of the various core technologies. So the maximum is the cold box. Is more than 60% of the cores produced in the world is cold box. I do not see, this is the as on 2000 data. So not much change has been happened in recent years, except the cold box is almost declining. This is the typical process flow of the cold box core manufacturing. I am going to talk about the best practices on each process in coming slides. So for the core simulation, core tooling design, tooling manufacturing, core box tooling setup in the machine, then incoming quality of the raw materials, sand mixing, then core manufacturing, after definning, core painting and drying, and storage and inspection and FIFO. This is a typical process of cold box. Phenolic binders, resin and activators are mixed with the resin just before use. Mixed sand is blowing into the core box by compressed air. Then amine is injected into the core box after blowing the to react and form bonding. After pouring, the binder bridges between the grains are weakened by the metal heat that the sand can be removed from the castings by light mechanical forces. Very fast and cost effective for large castings. The advantages of cold box: it is high productivity, low energy intensity, low startup and tool changeover times. Cores of high complex shapes can be made with this process. Then low tooling cost. These are the advantages. So first process, simulation. We do simulation of the cores to identify the formation of the cores with predefined shooting points and vent positions and ejector positions. All this has been designed in the design stage by simulation. Some of the design considerations: the minimum wall thickness for the core better formation, blow tube and size location are important for the good cores. Position of vents, air passage grooves, loose piece designs are very important for getting a good core. This is a selection of tool materials. Steel alloy and cast iron are best suited for core box tooling for high volume parts. It has good surface finish. Because it is good surface finish, will be helpful for core withdrawal and finish, and higher wear resistance with good thermal conductivity for better curing of shell cores. This is the blow tube designs for getting a good compacted cores. Blow tube size and location are very important. Large blow tubes reduces the impingement velocity of the sand, and it reduces the wipe off and deposit on the core box. Large straight and tapered ID tubes are preferred. And the blow pressure, lower blow pressure is preferred because it reduces the sand wipe up and sticking with the core box. Lower the blow pressure, less wear of the core box. Tooling must be designed to permit low pressure. That is more important. On the design stage, you should ensure the design is made for low pressure shooting. This is the nozzle design. The rubber tubes are provided over the nozzles. It helps to transfer 100% of kinetic energy during sand shooting, helps to avoid air pockets defects in the core, no pressure drop, no sand leakage, then you can reduce the shooting pressure. This is a typical core box design. This is a core box, sorry. This is the core box. This is the vent positions. These vents are self-cleaning vents are better. The vent area should be 80% of the blowing area is preferred to be cleaned regularly with air and special tools. Should be placed in core print areas wherever possible to avoid rework and in the casting profile areas. These are the sand parameters: grain size, grain shape, fine content in the sand, acid demand value, pH value, contaminants. These are all the important parameters to be controlled during the process. The grain size of the sand is best 50 to 60 AFS is best suited. Resin demand high with higher GFN number. Lower flowability will be poor with higher GFN number. Gas generation higher with higher GFN and low permeability. So grain shape, round shape is better for strength. Subangular sand is better for veining control. So combination of both these is better for core production. Then acid demand value best is 0 to 5. Usable we can use 5 to 20. The cold box resin reacts prematurely with the basic environment. Bench life shorter with higher AD value. You see the graph. So if higher this thing, it drastically reduces the bench life. pH value best as close to neutral as possible. It is important because higher basic sand will tend to shorten the bench life. The contaminants, clay and iron oxides, best low clay contents and oxides, usable 0 to 3 clay content as well as oxides is 0 to 3% is usable. Sand temperature, the best is 21 to 27 degrees centigrade, usable 10 to 40 degrees centigrade. It increases the temperature, increases in reaction rate in the sand hopper and leading to the lower bench life. Sand under 10 degrees centigrade will result in poor mixing due to thickening of the resin. So mixing will be a problem with the lower temperatures. So moisture, best should be close to 0. Moisture content in the sand deteriorates core quality rapidly because of moisture causes the following problems. Water reacts with activator, lessens flowability, lower core strength, hardness and bench life of the mixed sand. Need for excessive binder. Water is a disaster for cold box. This is a schematic diagram of the machine. Machine parameters always should ensure the parallelism of the core boxes and no gap after closing the core boxes. And maintain the sand level in the hopper as low as possible to get the good compaction of the cores. This is on the mixer side sand mixing control. Sand mixer type, vertical intensive mixers are best for cold box. Direct for mixed sand into the hopper is best. Then capacity selection is very important based on the consumption of the sand. Automated controls on sand, mixing time and resin additions. Periodical calibration of addition quantity and mixing time is very also has to be done. Ensuring sand mixer blades side and bottom gap. If these gaps are not maintained, the mixing will not be uniform. Protecting tank opening from moisture pickup. If you keep the resin tanks in the open condition, it absorbs moisture. So to avoid that, the tank should be closed. Consumed the prepared sand within 40 minutes. Pneumatic conveying of the sand increases the fines content. So it is better to separate the fines by effective removal of the fines. We have to find a way to remove the fines. More fines demand more binder. The normal binder addition varies between 0.5 to 1.5% of each part, depends upon the quality of the sand. Lower the binder addition, lesser the problem on castings. So this is on amine control. Amine vapor air temperature is important to have a uniform flow of amine gas. So 95 to 130 is preferred range. The warmer the gas carrier, the richer the catalyst mixture. The warmer the delivery pipelines, the chances of catalyst or moisture condensing as a liquid. If the temperature is low, it condenses and it becomes a liquid amine. So install amine gas generator closer to the machine to avoid again condensation. Optimize gassing chamber size for reducing the catalyst wastage. Air dryness is important since moisture condensate in the blow magazine. Moisture weakens the core by reducing the compaction. Moisture reacts with the activator and reduces the bonding strength. This is the typical gassing plate. It is as small as is better. The same blow magazine can be used for different core boxes by having the seal here. So the following is important to control the amine consumption. Grain size of the sand, temperature of the sand, composition of resin and activator, geometry of core, surface area of the vents and the core boxes, gassing chamber size, gassing condition, that is gassing pressure and temperature, dryness of air, sand moisture. These are all the important things for amine control. So recommended resin additions, 0.5 to 1%. Activator, many people add equal amount of activator. That is actually not necessary. You can add 80 to 90% of resin is sufficient. catalyst 10 to 15% of the resin. So this is the sum of the tests on the cold box in the process. Tensile strength, transfer strength. Actually, transfer strength is better than tensile, because in actual field the cores are subjected to tensile the transfer force. Then scratch hardness on the shop floor. This is a special test to find out the property of the sand. This is to identify the wearing with the different sands and different resins materials. This is the cone test. Similarly, to different core casting defects due to core can be identified with this test. Then core box maintenance. Ensure proper cleaning of the core boxes before loading and replace the vents if required during the run. Plating of core boxes for finish and wear resistance. Core box cleaning methods: chemical cleaning, ice blasting, mechanical cleaning. So this is some of the points for troubleshooting. Non-curing of cores. Check moisture content in the sand, amine quantity, resin, ordinary weight, leakages in pipes, core boxes, and avoiding adequacy of vents. Shorter bench life. Check moisture in the sand, sand temperature, and mixed storage conditions. Hard and soft core. Check binder ordinary weight, gassing time, and sand temperatures. Poor filling of cores. Increase blow pressure, increase venting, check vent regularly, change vents if required. Then coming to the shell core process. This is the basic of the shell core process. The process was developed in 1940 by Croning. The process is also called Croning process. Pre-mixed shell coated sand is used for this process. Best for light castings with better dimensional control and surface finish compared with other core production process. Excellent collapsibility and permeability. This is the advantage of this shell cores: better surface finish, dimensional accuracy, reduced machining strokes you can maintain. Cores with less than 2 mm core section thickness also can be made with this process. Very high bending and tensile strength, excellent humidity resistance, having higher shelf life, high temperature resistance and stability, superior waning resistance, good shakeout, excellent for critical applications like water jackets. Shell cores can be made all over, resulting in lighter weight and lower cost of cores. This is the important process parameters. Core box temperatures is, but in its best range is 250 to 300, because if you maintain more than this, the resin melting time will shorten and it will not melt uniformly. Then shooting pressure, shooting time, these parameters are important. Vent condition. So sand coated with a solid flake resin is better for flowability and dense packing of cores. Shell sand bag stacking height to be limited to avoid core lump formation. Avoid core over curing of cores may lead to penetration defects on the castings. Periodical cleaning of core boxes to avoid resin buildup and affecting dimensional. So for shell, we do hot tensile strength and transfer strength test. So for the visual, the better curing, this is the lower curing, this is the higher curing. This is the ideal curing of the cores of different sands. This is the monitoring of the shell thickness. This is the lower one, 5 to 6 mm. This is completely over cured. So this is the ideal curing. So this is for troubleshooting of the shell core process. Low core density, poor filling of cores. Probably low, increased blow pressure, provide additional venting. Surface of core brittle, increase curing time or reduce core box temperature to prevent over curing. Under cured core, increase the curing time, core box temperature. Over cured cores, reduce the temperature and curing time. Low core strength, increase the resin content. LOA of sand, increase in resin levels of sand. Cores too strong, reduce the resin content. Cores have thin-walled shapes, maintain an even depth of cure to adjust the curing by adjusting curing time and temperature. Blocked vents, check and clean the vents regularly. Moisture in air, check the drains periodically. Permeability of sand is too low. Use coarser sand. Resin buildup of core box, clean the core boxes. Spray release agents less often. Scoring marks in the core box. Repairing the core boxes on regular intervals. Dusty resin coated sand. Monitor the sand dust trapping arrangements. So then coming to the core coatings. So why coating is required? To get a smooth surface finish. This is without coating, this with coating. So coating is used to improve surface finish, metal penetration, sand fusion, to control veining, core and metal reaction, to cast blow holes, scabbing and erosion. To avoid all these things, core coating is required. The basic test carried out for core paint during the process: specific gravity with BMA, viscosity with flow cup, wet film thickness with gauge. This is the core coating and painting parameters. Ensure homogeneous mixing of the paint before use, because it contains a lot of liquids which uniformly has to mix to have a better performance. Use mechanical stirring for continuous mixing. Avoid excess stirring, high-speed stirring and foam generation. Follow periodic cleaning of tanks, mixers, stirrers. It is recommended to clean the tank every week to avoid biodegradation. Consume all the diluted coating within a week. Filter the coatings at regular intervals to separate sand particles fallen in the coating. Use the coating at proper viscosity. Do check and adjust viscosity periodically. This is the core storage and before. Core handling in the boxes is prepared for smaller cores. It should protect for damages. And in the shop floor, to avoid dusty environment, cores has to be kept in close condition. Shelf life monitoring. Cores should be consumed within the shelf life. So these are some of the energy conservation scope in core shops. Providing effective thermal insulation in the core drying ovens can reduce the energy consumption drastically. By optimizing the core oven drying temperature and conveyor speed. So by reducing the core trolleys in the oven, weight of the core trolley in the oven, so thereby you can reduce energy drastically. Here to install VVD for core oven and shell core heaters. And similarly, arresting the exit air loss, heat loss in the oven, and length of the oven can be increased, or going for micro heating ovens. So this scope for a lot of scope for reducing energy here. Install VFD for compressors and hydraulic power pack motors. So there is scope. Replace low efficiency motors with high energy IE3, IE4, IE5 motors. And in shell core shooters, the machine plate, in between machine plate and heater plate, if you provide the insulation, effective insulation, it reduces the energy. So that's all. Thank you.
Questions? Any questions? Please raise your hand.
What is the resin consumption at Breaks India? You are using
It's 0.7, 0.65. 0.7 resin, 0.65 activator.
consistently you are able to get strength.
Yes.
But it is only with imported sand.
No, we are almost we have stopped imported sand now. Gudur, to some extent we are using Mandovi sand, Gujarat. That is only 15-20%. Balance remaining is from Gudur. Immediate strength 20-25. Tensile 12 kg tensile. Huh? I am telling in kgs, 12 kg. Side gap maximum 5 mm, bottom gap 2 mm, 1 to 2 mm. 1 to 2 mm so bottom gap. It depends on the again weather condition. Normally we will not keep more than a week. But in the rainy season it deteriorates within 2-3 days. You have to paint it immediately.
What is the weight of the largest core you make in the core box?
15 kg.
1 pint.
1 pint. As currently we are making a maximum of 15 kg.
We-
50 to 60. Yes.
Any other questions?
So what is the selection criteria for cold box and shell mold?
What criteria?
Selection. To select, we want to go for shell molding or cold box.
It is. I think it is only a wall thickness. If the wall thicknesses are more than 5 mm, then definitely you can go for cold box. Recommended? Core baking. Okay. We operate at 150 to 180 degrees centigrade. Mostly we will not change it. Only the bigger cores, continuously loading more than 10 kg weight of core, continuous loading, then we will go for 180 to 200.
So the other remaining questions, I think we'll take it over the lunch. As we are running. Last question. Okay.
Pneumatic system AFS from bunker to the silo to the mixer. So there is a gradual deterioration in the AFS.
That's what. In the,
How to control that?
the sand delivered into the sand hopper. There you can put the extraction and remove the fines content.
Extraction.
Yes. And remove all the, it flows, no, dust it flows.
But it is going below 30 AFS. Then how to do that?
No, only fines generation will be there. It will not reduce the AFS number. It only deteriorates.
But in our case, we have seen that it is going down below 30 AFS.
What AFS you are getting?
So approximately it is going up till 45 to 46.
What is your input raw material? How much?
Input we are using around 45 to 50,
Okay.
but it is dropping down to 30 AFS.
I don't see any reason to dropping it down. Maybe selection of the sample, because while sand is falling, all coarser material comes outer. Finer materials will be inner. So if you collect it on the outer side, it will be coarser.
What do you suggest for that? Because while dumping in the bunker,
You should have a bigger size bunker.
bunker is big.
Okay.
While dropping it is getting happen. So how to maintain that? Because the raw source which is coming, it is blended and uniformly mixed on.
Yes.
So you need to balance it in bunker. How to balance that? That is the issue.
You can tell. Like he says, it is sand is falling on the bunker, and while collecting the sample, it is coarser. It cannot come. That's what I mean.
Sometimes it is containing that like that. We have analyzed it. At stage-wise, we have collected the samples and we found
Our experience is we reported suppliers many times as a coarser sand. They come and re-inspect that, and they evaluate our sampling method itself is wrong. So they told only like this. It is then we finally concluded that practice is wrong. So if you take the sample in the deeper area, it will be correct. So there is a method for collecting the sample. You have to follow that.
telling about the bunker and whatever you are telling the sample, that is part okay.
Okay, sir.
But the pneumatic system which conveys
Okay.
to the main silos,
Okay.
so at every location we find different GFL. If you collect
But-
there also, we are not getting the proper GFL.
Ever you have tried after it reaches the mixer?
Yeah, before the mixer also we have collected.
Like it, in the mixer. After falling into the mixer, I think it all mixed and come together.
That is the variation we are finding.
Okay, okay. Sir.
I think we can take the discussion on to the lunch
Yeah.
floor.
Okay, sir.
You showed one defect, white film defect.
That is a white layer. White layer.
White layer on the core.
Not on the core, it is on the casting.
On the casting.
Core paint sometimes. Yes. Yeah, we are doing. We are giving our all scrap sand to the cycler, and they are giving back to us after coating. No, we are getting it as a shell core.
Okay, so we'll have more questions over the lunch while networking. But I thank you, sir, because it's a very, very useful and informative presentation. With the amount of questions we have received, it tells us how useful it was. So now I request Mr. M. Armugam, Council Member, Chennai Chapter, IAF, to felicitate Mr. V. Baskar with the traditional Angavastram. Now I request Mr. S.